recording, just waiting for it to actually start. All right, recording has started. Chloe, go ahead and start. Julia, go ahead and start. I remember, Chloe, you're doing top half of the screen. Julia, the bottom half of the screen, or the middle to the bottom. You know what I'm saying. Julia, I'm going to guess that is a 4 and not a 9 because I see it's a 4 here. Is that a 4? Okay, that's a 4. Okay. So, Chloe, you said you did the monkey method and the box method, but I chose to show the box method. So I have never seen the box method before. Chloe, are you able to explain on mic if you have one? Like I understand, I can see what you did. I'm just kind of curious of how you derived these two numbers. Like I understand adding up to -11, but why?
Okay, I'm going to talk.
We hear you.
You can hear me?
Yes.
Okay. It's weird. My button doesn't say that it's on.
Oh, it's on.
Okay. So over here I have the sum, which is supposed to be the middle one minus 11x, but the product is supposed to be this first one times the second one, which is negative 60x squared. So I was looking for two numbers that added up to minus 11x and multiplied to negative 60x squared. So, and I found 4x and minus 15x. And then I found the common factor between these two numbers was 3x, and the common factor between these two numbers was x, and then I filled in the rest to multiply up to each one. And then I had 3x plus 4 and x minus 5.
That is an interesting method. Did any of you else that's in class right now learn this box method? I haven't seen it before. All right, well done, Chloe. Well done. Thank you. So I see there's limitations of this box method I can see. One being if your leading coefficients, right now it's a 3. If this was, let's say it was like a 6, an 8, basically a number that's not prime, I could see it being a problem to find combinations, maybe. But because it's a 3, it's a prime number, it's, well, 3 times 1 is 3. So that makes it easy here and here. My mouse is like super laggy. Okay, I don't know. It's my computer's lagging. Anyway, so I like this. I think it has a lot of good value for polynomials that have a really small or a prime leading coefficient. Julia, you did which method? Okay, you did factor by grouping. I like that. And you obviously had the same approach in terms of figuring out these two numbers. And the work that I'm about to show behind this blue shade here is the same thing. It's the same work that Julia did, it looks like. I didn't do monkey method for this work. I did by grouping. So same thing Chloe did. 3 times negative 20 is negative 60. So I have that over here. And then I listed all the all the products that multiply to, well, negative 60. So I got 2 and 30, 3 and 20, 4 and 15. One of them has to be negative, of course. And whatever combination that you find, it needs to add up to, well, negative 11, like Chloe said. So the only combination that actually adds up to negative 11 would be, well, 4 and negative 15, same thing that Chloe found. Hold on, let me see if I have anything open on my computer because it's super laggy. Like I can't even point, it's so bad. Hang on, sorry. Yeah, I don't know. So yeah, so I listed, you have your 3x squared, you minus 20 to the very end, and then you have negative 15x and positive 4x. And then this part is trial and error, whether or not the negative 15 in this case goes first or the positive 4 goes first. Well, if you try the 4, 4x and then minus 15, well, the next step's not going to work. So once I ordered these, you group them like I did in red. And then I GCF out of my first grouping a 3x out. And then for the second grouping, I GCF a 4 out. And if you notice, what's left over are factors that are the same, x minus 5 and x minus 5. So I put brackets around the entire thing, and I'm just showing that I can now GCF that entire binomial x minus 5 in front. And what you're left with on the inside, well, would be this 3x in the first term place, and then the 4 in the second term place. And then I just rewrite it without brackets. So that's how I did it, and that's factor by grouping, I believe it's called. Chloe did monkey method, but she also did the, I don't know, they call that Punnett square. And then Julia, I think you did solve by grouping or factor by grouping as well. So the good thing is, there's more than one way to factor. So you do the way that you like and it doesn't matter. We get the same answer. But the important piece is you know how to factor, because the reason why I'm going over this now on Bellwork is because we're going to use this in today's lesson at some point, and you need to know how to factor something like this. If you didn't know how to factor this, you're going to be in a world of trouble when we get to this problem. So maybe talk to me after class, email, Skype, and I can find you. We can go over some examples, learn how to do this again. I can show you some Khan Academy videos that are really good. But all of you should know how to factor. Okay, so today I have a lot of examples, but I only chose, it's like 1, 2, 3, 4, 5, 6, like 8 examples we're going to do out of like 22. All right, so this is day 1 of 4.04. We're going to solve trig equations. And trig equations, they can all be very different. All right, we're being recorded. Make sure you have your paper, pencil, pen, calculator. Also, make sure it's in radian mode. I think we'll be using that mode pretty much the entire day. All right, so some tips to solving trig equations. So we want to isolate the trig function. So if you have a bunch of signs in there, you want to get the signs on one side. So have out your trig identities paper that all of you should have downloaded and printed, or if you know them top of your head, because we're going to use these to eliminate trig ratios, and we'll see that. All right, and then you pretty much just solve as normal if it wasn't a trig equation. There are restrictions, and I think I have one example we're going to go over today of showing you what that restriction might look like if you come across it on a quiz or a test or your learn or practice module examples. And just like yesterday, dealing with problems that usually always just have sine and cosine, working with those, and even the final answer is ideal. It's usually easier when you do that. All right, so the problems that you see that I'm covering with red, we're not going to do those in class, but I would recommend snipping them and working them out on your own. And at the very end, I'll come back and I will uncover all the red boxes to show the work for the problems that I'm not going to be going over with all of you in this live session. I wish I could. I don't have enough time. Having a 2-hour-long class isn't very fun for anybody. All right, so number 1, these are going to start off pretty easy, then they get gradually harder. So kind of treat that secant theta as like a variable. It's x, right? So this is 6 equals negative 3 secant theta. What's the first step all of you think we should do? Yep, divide by negative 3. Yep, so everyone divide by negative 3. I did 2 things in one, sorry. I divided by negative 3, but then I also used our trig identities to convert secant into one of the 3 fundamental trig functions. Remember, secant is the same thing as 1 divided by cosine. Then Multiply both sides by cosine theta and also divide both sides by -2. You can do that trick I mentioned some time ago, recently, that we can just swap diagonals. So it saves us basically doing two operations by doing that trick. That trick is amazing, I'm telling you. Right. What's our next step? Yep, arc cosine both sides. Yep. Do arc cosine both sides. So this was kind of what I was hinting at last unit, and I kind of confused some people when talking about this on the review for the test, that doing this and typing this in, you hit enter, you only get one solution when talking about domain restrictions in regard to like inverses. So remember, inverses, to be an inverse, it has to, be a function past the horizontal vertical line test. So like last unit, we talked about the domain restrictions for all the trig functions. So that way, when you have the inverse, it still is a function. And we use those domain restrictions last unit to derive our single answers for, well, problems kind of like this. But for these problems, for my examples, my domain restriction is from 0 to 2 pi. It's the full unit circle. So for these problems, if you type this in your calculator right now and you hit enter, remember I want in radians, it's going to give you one answer. But we actually have two answers. So remember, cosine is what variable again? Cosine is the x. So this problem is saying the angle is equal to the arcsine of -1/2. So I want the angles in radians when x is -1/2. So everyone look at your unit circles. Identify where x is -1/2. Which two quadrants is x -1/2? Go ahead and say it in chat. 2 and 3. That is correct. So x is -1/2 in quadrants 2 and 3. You need to look at your unit circle to confirm. So in quadrant 2, what is the radian, the degree, what is the radian, the angle in quadrant 2? 2 pi over 3. So that is the first answer. And if you type in your calculator, that's the one that's going to give you. So looking at unit circle, what is the other degree, the other radian? 4 pi over 3. Yes. So you have to have your unit circle in front of you to do these problems. I don't have it memorized. I'd be impressed if any of you memorized it. So have it in front of you, identify where x is -1/2. And it's what you guys, the few people that said it in chat, 2 pi over 3 and 4 pi over 3. You lagged. Are they always reflections? Yes. I would say probably yes, Antonio. So Antonio asked, are they always reflections? Top of my head, I want to say yes. I'm pretty sure yes. Whether they're reflections in quadrant 1 and 2, 2 and 3, 1 and 4, or diagonals even, 1 and 3 or 2 and 4. So they are reflections in some sense. Yeah, so Katie, if you're lagging, we found this other radian angle by identifying where x, the xy coordinate, where the x value is -1/2 on your unit circle. So you should have this printed out. I have mine in front of me right here. Um, that's how you find it. All right, Katie, you good? All right, all right. All right, so I'm skipping number 2 to save time. I'm skipping number 3 to save time, but still snip it and work it out on your own. Again, at the very end, I'm going to come back and remove all the red boxes to show the work form. All right, number 4. Let's work this one together. All right, what should we do first for number 4? And there's more than one right answer of how you can approach number 4. Some ways obviously easier than others. So what do you guys think? What should we do? So Neil says arc secant. That's a possibility. Right, Sarah. Nice line. Square both sides. Well, if you square both sides, now we're going to have secant squared of that stuff. Is that even an option? I'm going to say it's probably a bad option. Yeah, maybe a trig identity. So remember, one of the tips would be usually getting things in terms of like sine and cosine would be good. So yeah, there you go, Antonio. 1 over cosine. So you want to rewrite that left side as 1 divided by cosine of that stuff. Looking at cosine and sine, just, I don't know, this makes me feel better. All right, what's next? What's next? Well, we can't. You can only do arc sine when you actually have cosine by itself. And we don't. We have a fraction. So you can't just arc cosine that. So flip them, basically. Use that little trick. So multiply both sides by the cosine, divide both sides by the radical to get this. Using that little swap trick will save you those 2 steps. All right, so then you can arc cosine both sides. Well, I'm sorry. Before that, though, make sure you rationalize 1 over radical 2 by multiplying it by rad 2 over rad 2, and that's how you get rad 2 over 2. So I didn't show the work, but all of you should rationalize this fraction to get you this. All right, then we can arc cosine both sides. So here's a little twist. This is why I'm going over this problem. We have the arc cosine of that stuff equals theta plus pi over 4. So what do you think we do? And maybe those 2 blue those blocks side by side is kind of a hint. Setting to 0. You could do that before I set to 0, I guess, or what you're kind of thinking. So Jacob says negative pi over 4. So what do you mean negative pi over 4? I understand what you're trying to say in phrases. So I think Jacob's saying inverse cosine of rad 2 over 2 is what? So if you subtract pi over 4 to both sides, then you would have arc cosine of that stuff minus pi over 4 on the outside of it equals theta. And sure, that's closer, I guess, right? That's closer. Let's save that step until the next step. So yeah, Emily, yeah, you want to find what arc cosine is using your unit circle. None of you should be typing these in, by the way, because if you type these in, it's just going to give you one of the solutions. And the interval I'm telling you for every problem is from 0 to 2 pi. So you need to use your entire unit circle, not just that domain restriction. So this is saying, well, remember, cosine is x. So I'm asking you, when is x radical 2 over 2? Well, you look at your unit circle, there's two quadrants where x is radical 2 over 2. Which two quadrants? Yeah, there, yeah, 1 and 4. 1 and 4. So in quadrant number 1, x is rad 2 over 2 at pi over 4. In quadrant 4, where is x rad 2 over 2? 7 pi over 4. Yes. So we see arc cosine here, so we better write what we get, and we get two answers here. We get pi over 4 and 7 pi over 4. If you're ever in doubt of these two being correct, you can type in cosine of pi over 4, hit enter, you will get radical 2 over 2. You can also type in cosine of 7 pi over 4, hit enter, you will also get rad 2 over 2. It's kind of a way to check going backwards, right? So now that we're on this step, now we can go ahead and subtract pi over 4 to both sides. And yes, we could have done subtract pi over 4 like some of you suggested first before doing arc cosine. But if I see arc cosine, I better actually write down what it equals. And it has two answers because we're using the full unit circle. So that's why I chose to do that before subtracting pi over 4. I didn't want to, I don't know, I guess confuse myself. But yeah, pi over 4 minus pi over 4 is 0. So there's your first answer. And 7 pi over 4 minus pi over 4 is 6 pi over 4. Reduced is 3 pi over 2. Yep. And to check our answers, what we can do. Hold on, I'm going to restart. Hold on, I'm going to quit and relog in. Hopefully it doesn't kick everybody out. Okay. Let's see if my mouse works better now. All right, to check our answer, we can plug 0 into theta and then type this in. Well, we couldn't type unless you have like a TI Inspire or a like TI 84. I don't think my Casio has the secant option, but good thing we know what secant is actually equal to. So I could type this second line in, and I would plug 0 into theta. And I would do 1 divided by cosine of 0 plus pi over 4, hit enter. I should get radical 2. If I do, it means 0 is correct. I would then go on to plug in 3 pi over 2 into theta right here. And I would do 1 divided by cosine of that stuff. Hit enter. I should also get radical 2. If I do, it means 3 pi over 2 is correct. So that's how you check your answers. On a quiz, on a test, even your work, you should always do that. All right. Number 5. What do we do first? Now remember, those trig functions is just like saying x. So if it helps saying to yourself, oh, that's x squared equals negative 3x squared plus 1, well, what would you do if it was just x's instead of like sine or whatever? Add, yep. So I would add 3 sines squared to both sides. Yeah. Combine like terms, right? Just like it was any other equation. So we're going to add 3 sine squared to both sides. So if I have 1 sine squared plus 3 sine squares, how many sine squares do I have? I have 4 sine squares, thetas. Yeah. Yeah, it's like a variable. If I have 1 and I have 3 and you add them together, I get 4. Okay. So now I combined like terms. Now what do I do? So remember, if solving equations, you combine like terms if you can. We did that. We're done. Now what? Divide both sides by 4. Yep. Because that's 4 times that sine squared theta. So divide by 4 both sides. Now what? Square root both sides. Yep. And when you square root both sides, what can't you forget? What can you never forget? Plus or minus. Yep. So the square root of 1/4 is 1/2, plus or minus. Don't forget that. Now what do we do? Arc sine both sides. Yep. Okay, now we have to go to our unit circle. And the question is, well, what angles? Now, remember, is sine x or y variable? Sine is the y. So the question is, at what angles is your y value either plus or minus 1/2? Which quadrants have y as being plus or minus 1/2? Which quadrants? All of them. Yes. All quadrants. So I should have how many solutions for this problem? I should have 4 solutions. You're right. So identifying all the angles that have y as positive or negative 1/2, you should get those 4 angles. Pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. If you just type in the arc sine of, well, 1/2 or negative 1/2, you'll only get, well, half of the answers. Isn't that funny? All right, I'm moving on. There's number 6 snippet and work on it later. My camera froze. Your face looks crazy for a second. Doesn't it look crazy all the time? Is it really frozen? Oh, I don't know. New Rose being extra weird today. So I'm skipping number 7, number 8, number 9, and number 10. What time is it? Gotta hurry up. All right, so this one, number 9. What do you think we do first? So I could see how you would want to divide by cosine, but you would be wrong. Identities. No, you couldn't really use identities here either. Like you could divide both sides by like, I don't know, sine and have cosine over sine, which is cotangent, but then you're like cotangent equals cosine, and that just, you're going in circles. So, Julia, I'm glad you asked. Why can't we divide by cosine? So mathematically, yes, we can, and they would cancel out. The problem is they cancel out. And if you cancel out like all the cosines by dividing both sides by cosine, you're actually um, you're you're dropping off answers by eliminating cosine. So we can do that, but we don't want to do that because then we'll miss those answers that involve cosine. So if you look at the title, the title of this slide says more complex equations, common factors. So we have to solve this by factoring. So what we really want to do, even though it's like it's screaming at us to divide both sides by cosine theta to make it 1 equals sine theta, we don't want to do that because then we lose half our answers by eliminating cosine. So we are going to subtract cosine theta both sides. And now we have cosine theta sine theta minus cosine theta. Now both terms have a cosine theta, so we can now GCF a cosine theta out. So what I'm going to do is, actually I'm going to write on my screen. So I can like put parentheses here, oops, and here. So what I'm doing is I'm going to GCF the cosine out in front of that parentheses to get this. And if I was going reverse, well, cosine times sine gives me back to this, and then cosine times -1 gives me back to this. Remember, when you GCF that cosine theta out, there's not a 0 there. There's a 1 there. There's a 1 in front of that cosine theta at the very end. So now from here, what do we do? Think back to like, I don't know, last unit or even like algebra 1 or algebra 2. Let me reword my question. What if that said 0 equals x times x minus 1? What would I do? What would I do? What would we set to 0? Set both factors, yep, both factors equal to 0. You are correct. So once you have it in factored form, which we do, we're going to set both factors equal to 0. So we're going to have cosine theta equals 0 and sine theta minus 1 equals 0. Now these become very easy by the looks of them. You just solve it like it was a super easy problem. Arc cosine both sides for this one. And now the question is, well, using the unit circle, cosine is what variable again? I know I've asked this probably 1,000 times already. X. So on your unit circle, I'm asking you, what angles is x equal to 0? What are they? Pi over 2 and 3 pi over 2. Very good. All right, now let's do the other one. So what do we do first on the setup on the right here? Add 1 to both sides, yep. And then arc cosine both sides. Now, sine is the y variable, of course. So on your unit circle, I'm asking you, what angle is the y value equal to 1? Is it just pi over 2? Only one place. You are correct. All right. Now, if you notice, we have some overlap. So in your final answer, we only have to write that 3 pi over 2 one time. So that means we actually only have two solutions, pi over 2 and 3 pi over 2. What's your question?
So I thought it was pi over 2 and you put 3 pi over 2 for the sign.
Wait, say it again.
Right now, everyone in chat was saying that the sign, arc sine 1 equals theta, was theta equals pi over 2, and you put 3 pi over 2.
Oh, you're right. You're right. Good catch. That's a typo on my part. Sorry. Yeah, sorry. Yeah, so arc sine of 1 is pi over 2, not 3 pi over 2. The arc sine of negative 1 is 3 pi over 2, which is not what that is. So yeah, pi over 2, good catch. But we still have overlap, so it doesn't change my final answer, thank goodness. So I got lucky. Very good. I know they're a lot smarter than me, that's for sure. They catch me at least, I don't know, 5 times a day of my mistakes. All right. So let's get this next one. And the next one, it just looks harder because, well, you have radicals and stuff. So remember, we're factoring. So everything is on one side of our equation. Now there's a few ways to approach this. And on the next page, I do number 10 a different way. So how do all of you want to do this problem to start? And I'll do it that way first. So plus 2 sine. So isolate the signs. Can we divide by the radical 3? No. So let's think of factoring. How can we? So everything is together. How can we like GCF this like we did on the previous problem? Sine theta, yeah. So you can GCF a sine theta out. So Jacob says change to 1 over sine theta, and I'm thinking Jacob's talking about the cosecant. So Jacob, you'd be correct. Jacob's idea would actually be easier, but I'm going to show that idea on the next page. Let's look at number 10 by just factoring it. So somebody said we're going to GCF a sine theta out. You also could have GCF'd a negative sine theta out, and that just would have changed everything inside to be positive. So that would have made this positive and that positive, and then this negative in front. You don't have to. If you just pulled out the sine theta like some of you suggested, that's how I did it too. That's okay. Our answers won't change in the end. The work will change slightly. Slightly. Okay, so once it's factored, what do I do? Set them equal to 0. Yep. All right, so one on the left, since we basically did one like that already on the number 9, I'm just going to show the work for it. Ooh, let me back up. I got deleting happy. Okay, let's try it again. All right. So like number 9, dealing with cosine, we got sine. Sine is y, so we got 0 and pi. So the thing is with, well, let me wait until we we do the second half of this problem to kind of explain. All right, so second half, what do we do on the right? Add 2 to both sides. Okay, then what? Then what do we do? Yep, divide by radical 3. Well, negative radical 3. What do we have to do from here, from this step? Rationalize. So we could do that. What else can we do? So think back to Jacob's idea. Remember the hints at the very beginning of this talk about using fundamental trig functions? Yep. So write it as 1 over sine. So cosecant is 1 over sine. You could also rationalize this on the right, but I chose not to, and you're going to see why in a second here. All right. So now what do we do? So skip rationalizing for right now. Multiply both sides by sine. So we can multiply both sides by sine. And we also need to multiply both sides by negative radical 3 and divide both sides by 2. But use that shortcut of swapping diagonals. It'll save you a lot of time. So we just swap diagonals, which we save basically 3 operations. We multiply both sides by sine theta. We multiplied both sides by negative radical 3, and we divided both sides by 2. So using that shortcut. And this is why I say skip rationalizing on this problem. We could have done it, but then if you rationalize 2 steps before this, and you get to here, you have to rationalize again. So now you're doing double the work. All right, now what do we do? We're almost done. Yep, arc sine both sides. So I want to know the angle when your y value is equal to negative radical 3 over 2. So look at your unit circles. Which quadrants is your y value negative radical 3 over 2? Which quadrants? Quadrants 3 and quadrants 4, correct. And what are those 2 angles? 4 pi over 3 and 5 pi over 3. So going back to the first half of the problem. So we got the angle of being 0 and pi. And we know that cosecant, the trig identity, is 1 over sine theta. Now at the angles 0 and pi, the sine of 0 is equal to what? What is the sine of 0 equal to? Yep, sine of 0 is 0. So you can always just type that in, or you can use your unit circle, but the sine of 0 is 0. Also, the sine of pi is also 0. So at the angles 0 and pi, if we use those as answers, we would have an undefined error. You can't divide by 0. It makes our equation undefined. So I talked about at the very beginning that you might have solutions that are, well, invalid, and this would be a scenario. And it's not easy to spot them. An easy way to spot them is if you went back to the original problem and plugged in all your answers to see if they work. Well, the ones highlighted in yellow, they work, but 0 and pi do not. If you plug those in, you're going to get undefined error. Got to be careful. Got to be careful. Always plug in your answers to verify they work. All right, okay, number 10. So I'm going to quickly show this. Jacob said convert cosecant to sine, and this is actually going to be the easier way to do it. So when you do that, cosecant becomes 1 over sine theta. And now, because we converted it, they cancel out. But if you think about it, sine and cosecant, they're inverses. So we should have seen right away, sine theta times cosecant theta, we should have known that equals 1, and we should have just crossed those off, right? But from here, we can say, oh, well, now it's obvious they cancel out. And the reason why we can do this is because we're not dividing both sides by a trig function to cancel it out. This is actually part of the actual expression itself on the left-hand side, the equation. So now we get down to this. And then from here and on, it's the same thing as the column on the right from the previous page. Doing it this way, we actually avoid the whole issue of getting those two answers that actually don't work by doing it this way, which is kind of cool, I think. It avoids that whole mess. All right, some of you probably have to go. So I'm going to go ahead and put the link to this in chat for you if you do have to go. Please watch this later if you have to go, because there's another concept in here that I haven't gone over yet that's important. So there's a link to the PowerPoint if you need it. All right, there's
really
number,
quick.
can
you go back to the last one really quick? So just to make sure I'm like clear on what's going on. So you did the 1 over sine as cosecant and then just multiplied it by the negative rad 3 sine, right? In that step? The first
in this
one?
step here?
Yeah.
Oh, wait, which, right here?
The one that has the negative radical 3 sine over sine.
So what about it?
So did you like you did turn the cosecant into 1 over sine and then just multiply that by the negative radical 3 sine?
Correct.
Thank you. I just wanted to make sure I was clear.
Yeah, sorry. All right, 11 and 12, I'm skipping these. You can snip them to work them on your own. Skipping 14, but 13. All right, this is a doozy. So I'm gonna quickly kind of go through the steps here. All right, so we want to try to combine like terms where we can, and I see. So we have a number, we have cosine squares, and we have cosines. So when you have terms squared, So we have a trig function squared, the trig function, and then just a number. That is telling us, well, it's a trinomial. It's like saying x squared, x, and a number. And we have to probably solve by factoring. That's a giveaway. So combine like terms, we're going to add cosine squared both sides to get this. Combine like terms, and I'm going to reorder. So cosine squared plus cosine squared is 2 cosine squared. And then I'm going to put plus 3 cosine theta and then plus 1. All right. So again, start from the top. I added cosine squared theta both sides. I combined like terms in that second step to go to the third step. And then I reordered, having my squared term first, and then my non-squared term with the trig function, of course, and then my integer at the very end. So the next step, we could leave it like this and then factor it like it was 2x squared plus 3x plus 1. Or we're going to do something to make it look different and just more pleasant to look at. This method, I want to say it's called U substitution. You may have learned it in Algebra 2. I don't know. I learned it when I was in school called U substitution. We actually used the variable letter U. I didn't. I just left it as X, something that we're familiar with. But I stated cosine theta equals X. And this is temporary. This step I'm doing right now is temporary. We're going to have to undo what we did. But wherever you see cosine theta, replace it with an X. So that first term becomes 2x squared. Second term becomes plus 3x, and then you're plus 1. And I'm doing this just to make it look easier, so we can now factor it like we did on bell work. It's the only reason why I'm doing this step. And it is entirely up to you if you want to do this. I don't know if the Learn modules do it this way. I don't think they do. But I think this makes it look easier. But anyway, so factor this. So we can use monkey method, that Punnett square, solve by, or factor by grouping. But I'm just going to quickly factor it like we did in bell work. So I get 2x plus 1x is 3x. And then 2 times 1 gives me my 2. So it's same as bell work. We're just factoring it. I group it together like bell work. For my first binomial, I can GCF a 2x out. And then on my second binomial, only thing I can do is really GCF a 1 out. So I'm just showing that. And now I can actually pull out an x plus 1 in front of the entire left side of the equation. And I'm left with, well, x plus 1 times 2x plus 1. So this is all factoring. All of you should know how to factor this. Everything from this line here down to here, all of you should know how to factor. If you don't, we need to talk after class. I need to show you some extra material to kind of get you caught the speed to this, because this is pre-calc. All of you should know how to factor. All right, now from this step, I then undo what I did with the x's. I now replace all my x's, well, with back to cosine theta. So I'm going to have cosine theta plus 1 and 2 times cosine theta plus 1. So I'm just undoing what I did. And I remember, I only did that step with replacement just to make it look easier. All right, so now it's factored. I set both factors equal to 0. And then I solve them both accordingly. I'm just going to show the work because the work is rather simple from this step. So we have 3 answers. Theta equals pi, and theta equals 2 pi over 3 and 4 pi over 3. So 3 answers. All right. Going on. Skipping these. Make sure you snip them to work on them later. I'm skipping these. Make sure you snip them. And I'll go back. Number 18. So I'm going to quickly go through this one. We're almost done, by the way. All right. So we're going to use the Pythagorean trig identities here. Now, if you notice, I have cosine and I have a sine squared. So this one's different than the one we did before this, where we had a cosine squared and a cosine and a number. Here we have a sine squared, and then we have a different trig function, cosine. So that kind of tells us we're not going to probably do factoring at all. It's a good chance we're going to use trig identities. So you want to look at your, in this case, Pythagorean identities, and you only have 3 choices here. So you kind of look at this and say, well, which one of these might work? And I think only one of them kind of shows similarities. It's definitely not one involving cotangent or cosecant, the one involving tangent or secant. The first one, sine squared and cosine squared. This looks like the most promising. So we want to make all the trig functions to be the same. Right now we have cosine and we have sine. So we want to make them match when solving these trig functions. So we have to change one of them to the other. Ideas? What can I do? Ideas? So we're using the first identity. So that is a given. So what am I replacing with? So I want to somehow make the problem look different, but obviously have the same value. So what can I change? What for what? I'm going to give you a hint. Focus in on that sine squared theta. So let's use the formula, and I want you to rearrange the formula to make it look different for our needs. All right, some of you are scratching your head. All right. I'm going to replace sine squared theta with something, and that something is going to be whatever I solve for here. So I want to solve for sine squared theta. So I want to subtract cosine squared theta from both sides in my formula to give us this. So now sine squared theta is equal to, whoa, why is my pen drawing crazy? Well, that was cool. That was awesome. So awesome. Okay, so sine squared theta is equal to this. So I'm going to replace sine squared theta in my original problem with, well, what it equals to, based on that identity. So I write 2 cosine theta equals -2 plus, and now sine squared theta becomes 1 minus cosine squared theta. And now our problem has just one trig function, cosines. Pretty cool, right? Pretty cool. So now we have a cosine squared, we have a cosine, we have an integer. Now this kind of tells us we're probably going to have to factor. Maybe. Let's find out. All right, so combine like terms. -2 plus 1 is -1. So I'm going to add 1 to both sides. I want everything to be on the left-hand side. And then I'm also going to add cosine squared theta both sides. Okay. So I did two things. I combined the integers together, and then I also moved them to the left-hand side. I also added cosine squared theta to the left side as well. Now I want to reorder to have my cosine squared first, and then my cosine, and then my integer. All right, so now it's in this form. And now I do that U substitution, I call it again. Cosine is now x, so I replace all my cosines with x. I factor this. It's pretty easy. And now from this step, I replace all my x's with, well, cosine theta again to go back to what we were. And then we set them equal to 0 each. But they are the same, so I only have to do it once, which is kind of neat, right? And subtract 1, arc sine both sides. And where does x equals -1? Well, that equals -1 at pi. So there's your only answer. Not bad, not bad. Okay, let's go on. All right, skipping these. Okay, we got like 4 slides left. Okay, so approximate solutions. So we've been using the unit circle up until this point. Well, the problem is going forward from this slide up. We're going to have decimal values. So it makes it a little bit more tricky to look at. Maybe it just looks kind of confusing. We have to draw diagrams to help us out. Look at one. All right. All right, 1.86 equals -2 sine theta. Again, my interval is the entire unit circle, entire revolution. So we're probably going to have two answers. All right, we do what we did before to solve for sine. We're going to divide both sides by -2. We're going to arc sine both sides. All right. So I already created my circle, but you know what? I'm going to cover it up so I can draw the circle again and explain as I'm doing it. It'll make more sense if I do it from scratch. So let's do this. Whoa. All right, let's try that again. Okay. Well, I can't make a hollow circle. Okay, so I'll make that color. All right, and then I have my x-axis and I have my y-axis. Sorry, they're connected. I don't know why. Why does Numero hate me so much all the time? Okay. So the question to determine which quadrant these answers are in. Remember, arc sine, I'm asking you, I want the angle of when your y value is negative. All right, so looking at quadrants 1, 2, 3, and 4, which quadrants is your y value negative? quadrants 3 and 4. So because it's in quadrants 3 and 4, my angles are just going to be drawn in those quadrants. And I'm just putting them there just to show they're in quadrants 3 and 4. The angle's probably not correct. So now I'm going to type in the arc sine of negative 0.93, and I'm going to have it in, you can have it in degrees or radians. I do mine in radians because your answers on your quizzes and your tests, they'll want it in radians. So when I type it in, I get negative 1.194 radians. Well, I have a hard time visualizing radians, so I convert this to degrees by multiplying it by 180 over pi. So that gives us negative 68.435 degrees. So, and that shows in quadrant 4. So let me, and that's a negative. So this is why this one's confusing. This one is a negative angle. So that means it's going clockwise. So there is that angle here. Now your answer needs to be in an angle that is, well, positive, and not a coterminal angle. I think it might be true. So basically, think back to last unit. I'm going to use a different color here. So I want the angle starting from 0 and going all the way around to here. And we know that my blue angle that I drew in is negative 1.194. Negative 1.194. So how do I calculate the actual angle that's positive going to that terminal ray? So from last unit, so add 360 to it. Yeah, so we do 360 basically minus that angle absolute value, or to take the negative angle plus 360. It's the same thing. So that's exactly what we do. And that's from last unit. So we, and again, radians, we do 2 pi is a full revolution, and then we're going to do minus the 1.194. And that's how I get 5.089. And I put this in red outline, yellow text. Rounding work is bad. And I'm saying that because I was really upset when you guys were rounding your work on your TGA. So I'm showing this. You don't want to do this. My rounded work is this right here. My 1.194, that's rounded work. By me plugging this in right here, I'm using rounded work to get a rounded answer. We don't want to do that. So rather than use 1.194 right here, what do I want to use instead? I want to use the arc sine instead. Yeah. So that way I'm actually using exact values. And this is the absolute value, of course, because remember the arc sine of that negative 0.93 gives us a negative number. So it's 2 pi minus the absolute value of the arc sine of that. So now we're using, our work is actually exact values. And then we're rounding the final answer of how we're supposed to do it. In this situation, using rounded work and using exact work for a rounded answer yields the same answer. So we got lucky in this case. On your TGA, it happened the same way. Rounded work versus exact work, you got the same rounded answer in the end. All right. So next, I'm going to use a different color. Let's use, I don't know, I'll use whites. See how white looks. So now I want the angle from here to here. So looking at it graphically, how do I calculate that measure, that angle measure? Well, I'm going to give you a hint. A half a rotation is pi, and then that little sliver is going to be that 1.194. I gave the answer away. You add them together. The absolute value of that arc sine. So that angle is going to be pi, half a rotation, plus that little piece. Remember, like Antonio said, they're mirrors of each other, and that's probably true all the time. So that little sliver is going to be that 1.194. But again, I'm using rounded work in this step, but I'm only doing this just to show it, because using rounded work is easier to like look at and understand. But really, we don't want to use 1.194. We want to use the absolute value of the arc sine to get that. And it so happens we get the same answer, whether we use rounded work or exact work. So the answers we get for the angle would be 5.089 radians and 4.336 radians. To check your answer, you would plug those values into theta here. So I would have -2 times the sine, and then you would type, well, these in, hit enter. Again, make sure you're in radians. When you hit enter, you should get approximately 1.86. It's going to be an ongoing decimal, but it's going to be very close to 1.86. And then you're going to plug in 4.336 into theta, hit enter again. You will also get really close to 1.86. That's how you check your answers. So these problems require drawing diagrams. All right, I'm going to show you one more. So here's the work. Here's this one. Snip this one. Work on it later. I'm going to skip that one. I'm going to skip this one. I'll do this one. Okay. I'll do it real quick. Real quick, just to show the work. All right. So subtract 2 both sides. That's a given. Arc cosine both sides. We get this. And then I'm asking you, what angle do we get when x is a positive number? Well, x is positive in quadrants number 1 and 4, so that's why I drew those 2 lines. And then just to type it in, you hit enter, you get that angle in radians. Degrees at 71.941 degrees. So that's in the quadrant 1. Oh, I put quadrant 2. Why did I do that? Yeah, it's a typo. That's quadrant 1. Won't my pen work? Oh, it's white. Okay. That should be a 1. All right, so the angle is 1.256, and that's this angle right here. So my red angle is your first one, and thankfully, because we're in quadrant 1, I don't have to do anything else to that angle. It's positive. It's not a coterminal angle. So there's your first answer. Now the second answer, it's in quadrant 4, so I want that full rotation that I drew. So so from here all the way around to here, what is that equation we have to write? same as the previous page. It's going to be the 2 pi minus that given angle. So you might have to look back at your last unit's note for those formulas, but we're doing the 2 pi minus theta, or not theta, but the given angle to get 5.027. So I'm showing this example because using rounded work, I get this rounded answer. But when I use exact work, and I'm subtracting arc sine of 0.31, I am off by 1/1000th of a point. So if you happen to type this in your quiz, your test, it'll be wrong. And if I was grading it, it'd be wrong. I mean, you got to use exact work and then round your final answer. So in this example, it actually matters, right? So anyway, that was fun. All right, so I'm going to go back. I'm going to uncover all of the answers for the ones that we skipped. And that way you can work on them later. And you need to work on them for practice. The learn and practice modules don't have enough examples. So let me go back to the very beginning and start uncovering stuff. So number 2. There's that answer. Number 3. There's that answer. Number 6. There you go. Number 7. Number 8. $11 and $12. There you go. Number 14. $15. $16. $17. That's a long one. Yikes. 19 and 20. $23. $24. Oh my gosh. All right, guys. Well, that's all of them. So thanks for hanging around, and I hope you learned something.